Now that we have a class and an object, and we can see how it works in code, we are going to have to talk about a few things with regards to variables and how they're represented in memory. We're going to talk more about this over the coming weeks. But let's get into this in some depth because this does affect how you interact with instances of objects. So let's suppose you have a variable declaration, x equals 10. What happens inside the computer? When you declare a variable x equals 10, what happens? Well, the interpreter or compiler, depending on your language, says, oh, okay, well, they need a variable. So we're going to find a free slot in memory, and we're going to assign the name x that slot in memory. And so, right, this is our memory diagram. We have memory going, left to lower values, lower addresses, right to higher addresses. And we can move in between these, and x is assigned to this memory address. But where's the 10? Okay. And there are different answers to this question. In Python, the answer is that it's somewhere else in memory. In Python, a variable name is a memory address, and it references the address of the information because everything is an object. So we've got no data at X other than, hey, the memory address. That's it. And we saw that in our when we created our credit card class, and we instantiated, and we saw, credit card at, and then the memory address. This seems like a little bit of a pain that we don't have any data here. All the data is out somewhere else. So what do we think? Do we think this is universal? So while I'm playing Blue's Clues with y'all, the answer is no. I wouldn't ask that question if it were. There are different ways of storing variables in memory, and that affects how you manipulate them and how you have to interact with them to change them. So primitives, pointers, and references, 3 different ways languages can handle variables. And the simplest way, obviously, is a primitive. In a primitive variable, information is stored right at the memory address. So instead of storing 10 out somewhere else, it's just stored at X. And this is wonderful when we have very simple data types, because those data types are static in size. So when we allocate our memory, we can just allocate the size of memory for our variable. But it also means that we not only need to have a static sized piece of information, but we need to know how big that information is going to be. We need to know that we're storing an int, or a double precision floating point, or a 64-bit int, or a bit. We can't have this dynamic definition of a variable. So this is real common in lower to mid-level programming language. It's not real common in high-level programming languages, especially dynamically typed programming languages. It's real common for simple data types, ints, chars, floats, things like that. This is great. It's very fast if we can use it, but obviously you can see the limitations. Can't always use them. So the next step up is a pointer. And how a pointer works is, instead of storing the data at the memory address, it stores the memory address in the bucket, and it tells the computer, hey, the actual data is out here, and it'll dynamically allocate the necessary memory. Pointers are the next level up. References are the next level up from there. They are similar in that they both store the memory address where the value is actually stored. The difference is that pointers treat the memory address like any other data. It's just a number. It might be a really big number, but it's just a number. So with a pointer, you can add 4 to it like this, and that will move the address up 4 in memory, 4 bytes in memory. So you'll just read from, 4 bytes further up in memory. This is great. And it's really efficient, except it's wildly powerful. So imagine that instead of having plus equals 4, imagine that it's just, you mistype it and it says equals 4. Well, now all of a sudden, you're referencing somewhere very, very, very low in memory. Now, if your system isn't secure, or if you're using something like C, and I don't know that you can do this anymore, but this can be a problem because very, very low memory is typically used for BIOS and operating system information. So if you were hypothetically a high schooler in the mid-90s and learned to code C and made this exact typo, theoretically you could overwrite, I don't know, the boot sector of the very low memory, which would then get rewritten to the hard drive. And essentially, once your computer crashed, because any sort of low memory like this is eventually going to cause some sort of memory corruption. Once your computer crashes, it could restart the computer, and then when the BIOS tries to find the boot sector of the hard drive, goes, no, you don't have an operating system. Please reinstall. This actually happened to me. This actually happened to me in high school. So this can be dangerous, but it's very flexible. It's very dynamic. So languages then said, okay, well, let's make it a little more secure. Let's use references. So the difference is that the reference, while it still stores the memory address, it also stores additional information about what's in the memory address, including things like variable type, and also restricts the programmer. So you can't directly manipulate the values in memory. This is to prevent what I did when I was younger, and also things like buffer overflows, or, attacks that manipulate memory by just, hoping that people don't check boundary conditions. So in languages where you have pointers, you are exposed to that sort of attack. Languages with references, while not 100% secure, are at least secure from those sorts of attacks. So languages like Python, Java, they use references. Languages like C, C++, they use pointers. So we are going to use, we're going to be thinking about our information as references in Python. Okay, so why are we talking about this now? Well, we're defining methods, and we need to understand how passing variables into methods works on a low level. Okay? Now remember, when we take our arguments and we map them into our formal parameters, we are copying things into those variables, into those parameters. It's similar to when we just assign something to, when we say x equals 5. So let's get into that. What does it mean to copy or pass a value? So when we say the line x equals y, that means dump the contents of y into x. Take whatever's on the right-hand side and dump those contents into the variable x. But contents, what are the contents? Well, we just talked about it. In Python, variables are always references, right? And references are, at their core, the memory address. So what are the contents? It's the memory address of the information y is holding. So y is just a bucket that stores some memory address, and somewhere out in resident memory somewhere is the contents of Y. So when we copy the data, we copy the memory address. And when we pass a variable into a method, this is what gets copied, the memory address. So the memory address is copied into the function. Now, even though this is a reference, right? Even though the variable is a reference, what is inside of it is some number. And that is the thing that is copied inside of the method or the function call. So this is called passing by value. The value of the memory address is copied from Y to X. The value of the memory address is copied from your constructor call into the constructor. And what this means is you can alter what's at that memory address if what you're copying in is mutable. If you have a list and you pass it into a method or a function, and then you call append or delete on it, and then you look at your memory address, you look at the contents of your memory outside of the function after the function or the method completes, your list will contain the changes that happened inside of your subroutine. So this is what x equals y does. So copying a variable isn't really copying a variable, right? It's copying a variable, but not the object. So how do we copy objects? Well, you got three options. Option number one is aliasing. And that's what we just talked about, x equals y. It copies a reference of the copied object, and it results in two references to the same bit of memory. Okay? So that's one thing that we can take a look at. The next thing that we can take a look at is a shallow copy. And what a shallow copy does is it creates a new instance of our object, but only copies original references to the internal data. So what this means is if we have an object that contains a reference to something out here and a reference to something over here, right? And it contains a list, right? And it contains some number. And then we do a shallow copy of this object. Right? If we do alias, right? X equals X refers to this. If we do an alias, Y will also refer to that. If we do a shallow copy, Y will refer to a new object. But inside the object, it will reference the same two pieces of information. Okay, so you get two separate copies of objects. The objects are different, right? This is one object. This is a second object, but their internal references are the same. And then we can do a deep copy, which copies the structure of the object and then does a copy of the internal data. We can see what that looks like, right? If we say x equals y, x equals 1, 2, 3, right? X equals y, or y equals x rather. Y equals x, right? X, y. Hex ID X. Same memory address, right? That's great, right? If we say X equals list. Y was the second one. So we'll do Y equals list X. X is Y, false. Different memory addresses, right? Hex of ID of X, right? Hex of ID of Y. Different memory addresses. But let's change what's inside X. Instead of X being a list, let's make it a list of lists. So the first element is going to be a list which contains 1. And the second element is going to be a different list that contains 2. And the third element is going to be a different list that contains 3. Right? And let's do it again. Right? Different memory addresses. But X of 0 is a list. Let's append. Dot append 8 or here. I. We'll make it real explicit. Cool. What? How'd that happen? Well, what we did was we created a shallow copy. This creates a shallow copy. It gives you a new outer list, right? But it doesn't create a copy of the elements internal to the list. So each slot here, each slot contains its own reference that is copied over to Y. So if we say, instead of hex of X, we say hex of 0. We do the same thing with Y. We get the same memory address again. Cool. So let's try this one more time. Y equals an empty list for L in X, right? For each list in X, Y dot append equals list of I. This is going to say, hey, for every single element of X, take the values inside and create a new list and append that to Y. Whoop. And then we'll slam that on the end to break my code. Did I do wrong? Oh, L. Duh. Cool. Now, one more time. X is Y, false. Hex of X, hex of Y. Different. Hex of X sub 0, X of Y sub 0. Different. X sub 0 dot append, X sub 0, Y sub 0. Right? Aliasing, shallow copy, right? This represents a shallow copy, right? That's what this is. Deep copy. That is the difference. So, how are parameters and functions and methods handled? How are the arguments passed into formal parameters handled? They're handled through aliasing. So if we pass immutable objects, we have to expect changes can happen, so we have to be careful. If we want to create a shallow copy, as we saw with the list, we call the constructor of the object. Right? That creates a new object. You might have to program your constructor to take an instance of, whatever your object is, and strip out the values and create a new object, but that is the proper way to create a shallow copy. And the way to create a deep copy would be to implement a method called deep copy that would do what we just did, right? Would do a deeper, more granular copy of the object. Okay. One last thing before we get into inheritance, because magic methods are a key concept, and goes between visibility modifiers like public and private, kind of deals with inheritance, but also deals with all this other stuff that we've been talking about, okay? Why are the underscores there? Why are the dunders there? And when it comes right down to it, all objects have a set of hidden methods that control how the object works in Python. If I were to create a class called DumDum, and it inherits from nothing, and it contains nothing, right? That's it. D equals DumDum. If D is a DumDum. D dot under init. Hey, that worked. That's there. Huh, why? Well, there's a whole set of methods that exist that Python looks for in an object that the main object, the object that all objects inherit from, even ones that we don't say, hey, you're inheriting from it, will inherit. For instance, dunder init controls how objects behave at initialization when the constructor is called. Okay. I will bring up examples of these magic methods as needed. But the initializer defines how an object works at initialization. All you need to do to make your object act specially is create a new dunder init method and then provide the parameters and define behavior. So the specifics of all the magic methods and all those things are outside the scope of this course. However, if you want to know more about them, you can, go here, and that is a link to a relevant page that will give you all sorts of information on magic methods, how to use them, what some of them are, what they do, all that sorts of stuff. And as well as this one, which is the actual Python documentation on magic methods. But if you know what you're doing, then you can say, hey, like d.dunder le dunder 1, and it'll say not implemented because it exists. LE is not implemented. LE handles this. What I just typed was essentially asking for that. Right? Now, it's not supported between dum-dums and ints, but if we had implemented it, it could have been. Let's see. I wonder if I can do this. I wonder if I can get the same not implemented by saying this, and then saying this, and then that. Yep. Oh, sorry. That's the wrong one. Let's try that again. Okay. So, calling it directly like this, we at least get the not implemented. But remember, this is not how you're ever going to use it, right? This is not how you're ever going to use it. There are lots of magic methods, right? With our initializer, we can define that here. Right? Let me implement dum-dum for a moment, and I'll define our initializer. And we'll just define that. And we'll say self dot count equals 0. And then we'll say def dunder len and we'll say self dot underscore count plus equals 1, return self dot underscore count. So every time we call the dunder len method, it will add 1 to our count and then return that value. So we can say that. And when we do this, right, it runs the initializer. Python knows that when you call this, one of the things that you look for is dunder init. Then when you call len, it knows to look for dunder len. Okay. When you put a less than, it knows to look for dunder le. When you put a greater than or equal to, it knows to look for, I guess it's lt. I guess this is less than or equal to. And this is, yeah, that's less than or equal to. And GT would be greater than. So yeah. And that, and you had LT defined, it would run the LT method, whatever you defined. Okay. So that's what makes them magic, is that they have a special meaning to Python, a very limited, but also extensive set of methods that you can just naturally override. So if you have more questions about that, you can take a look at those 2 links. Otherwise, I will be bringing them up periodically during this class as they are helpful and as they are needed.